Hello students, welcome back to the third lecture of fluid statics, in which we are going to discuss about hydrostatic forces on submerged bodies in curved surfaces. Myself Praveen Yadav, assistant professor in mechanical engineering department. So in last lecture we have discussed about hydrostatic forces on submerged bodies, that is of inclined surfaces. And previous to that, we have discussed about horizontal surfaces as well as vertical surfaces. Now, this is the last lecture of hydrostatic forces on submerged bodies, that is of four type curved surfaces. Actually, what happens with respect to curved surfaces, that we are going to discuss at here. So, before starting to the topic, we'll discuss about the learning objective. Again, the learning objective is to know about the total pressure and center of pressure of curved surfaces and to know hydrostatic forces acting on the submerged bodies for curved surfaces. After end of this lecture, you will be able to explain total pressure and center of pressure concept, as well as you will be able to explain about hydrostatic forces on submerged bodies, that is curved surfaces. Now, curved surface is somewhat difficult and challenging surface for studying the fluidistic forces because it will not give the direct value of pressure P acting at any point. So, consider this is the curved surface of LM submerged in a static fluid as shown in figure. At any point on the curved surfaces, the pressure acts normal to the surface, and thus if dA is the area of small element of the curved surface laying at a vertical depth of h from the surface of the liquid, then the total pressure on the element area can be given as P is equals to dP, and this total pressure can be calculated as P into dA. Now, what is P? P is nothing but the pressure W into rho GH. Sorry, not W, rho GH. And here rho G is nothing but W. So, pressure P is nothing but W into H. And the cross-sectional area is dA. Now, this force dP acts normal to the surface, and further integration of equation would provide the total pressure of the curved surface at here, and therefore total pressure P can be given as integration of W into H into dA. Now here W is nothing but the specific weight, it is constant, it will comes outside. Now how to get the integration of H into dA? How to get integration of H into dA? It is not an uniform surface, that is which is previously we have studied for the horizontal surfaces, for the vertical surfaces, or for the inclined surfaces. It is the curvature surfaces, and everywhere the direction of pressure force will goes on changing at here, and that's why integration of H into dH for this curved surfaces is not possible. But in this case, curved surfaces, the direction of the total pressure on the elementary areas are not in the same direction, but it is varies from the point to point, and thus integration of equation for curved surfaces is impossible. And therefore, the problem, however, can be solved by resolving the forces P into two component of forces, that is horizontal component of force and vertical component of force. That is, we have to calculate the horizontal component of force PH and vertical component of force PV, perpendicular PH parallel to the surface of liquid and PV perpendicular to the surface of liquid. And from that, resultant P can be calculated as P is equals to root of PH square plus PV square. PH square plus PV square. Now, how to calculate this angle of inclination alpha? So, for that purpose also, the direction of resultant force P with the horizontal is given by equation tan theta is equals to PV by PH. And therefore, theta can be calculated as tan inverse of PV by PH. By this, it can be possible for us to get the value of PV by PH. Now what is pH? pH is nothing but the total pressure force on the projected area of the curved surface on vertical plane, and PV is nothing but the total surface pressure forces on the projected area on the curved surface on horizontal plane. That is, PV acts in a downward direction, pH will act in a horizontal direction. Now consider this is the quarter circular curvature surface immersed up to the distance somewhat s. Now consider SO be the depth of immersion, OM be the vertical plane, OL be the horizontal plane. Let X bar be the center of gravity of the surface and H bar be the center of pressure at where the pressure is actually acting on the body. Now area for OLM can be given as pi r square by 4. This is nothing but the area of this curvature surface. And for LM curved surface, projected area is equals to OM for horizontal forces. Projected area for LM curved surfaces is OM. Now consider the semicircle. Then the area LMN can be given as pi r square. Area LMN can be given as pi r square. Why I told you this? Because this is required for the calculation of horizontal forces and vertical forces. It is required in the calculation of horizontal forces and vertical forces. Now consider this is a problem on the same area curvature surfaces. Figure shows a curved surface LM which is in the form of quadrant of a circle of a radius 3 meter immersed in a water. If the width of gate is unity, then calculate the horizontal and vertical components of the total surface acting on the curved surfaces. Horizontal and vertical components acting on the curved surfaces. Now here see carefully, this is the curved surface LM. We already studied. In front of this OM be the vertical plane over which horizontal pressure forces are acting, and OL be the horizontal plane over which vertical forces are acting. Now it is immersed in the up to the depth of 1 meter, and this distance OM is given as 3 meters. This distance OM is given as 3 meters. That is, R is nothing but 3 meters, and therefore OM is equals to OL is equals to 3 meters. Now therefore, referring to the figure, distance OL is equals to OM is equals to 3 meters, and therefore horizontal component of total forces PH can be given as horizontal force PH exerted by water on the gate is nothing but total pressure force on the projected area of curved surface LM on a vertical plane, that is nothing but OM. So total pressure force on OM we have to calculate it. So it is nothing but OM into 1, because projected area of curved surface on vertical plane. So PH can be given as W into A into X bar. But A is nothing but this OM distance into 1. Therefore it is equals to 3 meters square. X bar. Now here X bar is nothing but 1 plus 3 by 2, that is R by 2. This 1 is nothing but initial distance plus center of gravity is nothing but R by 2, and it is nothing but 2.5 meter. And we know that W is nothing but rho into G. For water purpose, rho is 1000, and G is equals to 9.81. And therefore PH, that is horizontal forces, can be calculated as 73.57 kilonewton. Okay, so from this problem, first half part is over, that is calculated the horizontal forces with respect to the plane OM. Similarly, for the vertical forces, I think vertical forces is also asked now. Okay, initially we will calculate the point of application of pH. Now for point of application of force, we know that H bar is equals to Ig divided by Ax square plus x square for vertical plane purpose. And therefore Ig is equals to moment of inertia of OM about the center of gravity. So it is nothing but BD cube divided by 12. Now here B is equals to 1 and D cube is equals to 3. So Ig can be given as 2.25 meter raised to 4. So H bar can be given as 2.25 divided by A is nothing but 3 into 1, 3 meters into X bar is 2.5. So H bar can be given as 2.8 meter from the water surfaces. And therefore H bar can be located at the distance of 2.8 meter from the water surface. Now vertical component of the force PV. Now for vertical component purpose, we are going to consider a horizontal plane OL. So for PV purpose, weight of water supported by LM up to free surface is equals to weight of portion ULMOS. That is, for vertical forces purpose, it is required to consider this whole forces from ULMOS. These total forces are required when consider. And how to consider this? So it is nothing but rho into G, that is density into gravity into volume of this square ULOS, volume of ULOS plus volume of LMO. So volume of ULOS is nothing but UL into LO, because we are going to consider the immersion width is equals to 1 meter. Depth is equals to 1 meter. So volume can be calculated as UL into OS plus for this quarter circular portion, the volume of LOM can be given as pi r square divided by 4 into 1. Pi r square divided by 4 into 1. And here it is OL into UL into 1. So it is nothing but 9.81 into 1000 is nothing but rho into G. UL into OL, it is equals to 3 into 1, 3 plus pi into 3 square divided by 4. So 3 pi square by 4 into 1 is nothing but 7.068. So therefore final PV can be given as 98.77 kilonewton. Now this is another problem where a figure shows a gate having a quadrant shape of radius 1 meter subjected to water pressure. Find the resultant force and its inclination with the horizontal. Take the length of gate as 2 meter. Length of gate as 2 meter. Now here directly the length of gate has been given, it is equals to 2 meter and radius is equals to 1 meter. So for this problem purpose, again we will initially calculate the horizontal forces. We know that radius r is equals to 1 meter, length of gate is 2 meter. Therefore PH is nothing but the horizontal force acting on a vertical plane. So it is nothing but force on MO and it is equals to WA into X bar. Here A is nothing but area of MO. So area of MO is nothing but 1 into 2 meter. That is, they have given that length of gate is 2 meter. So A is equals to 2 meter square. X bar is nothing but L by 2 or R by 2 actually, and it is equals to 1 by 2 is equals to 0.5 meter. And W is nothing but rho G. Since this gate is provided for water, so we can say that it is 1000 into 9.81. So it is 1000 into 9.81 into 2 into 0.5. So pH can be given as 9.81 kilonewton. Okay. Now vertical force PV. PV is nothing but weight of water supported by LM. So it is nothing but W into area of LOM and into depth 2 meter. So it is nothing but W into pi r square by 4 into 2 and W is nothing but 9.81. So it is 9.81 into 1000 into pi by 4 into 1 square into 2. So it is 15.4 kilometer. So the resultant force acting on the gate P is nothing but root of pH square plus PV square. So we have the value of pH is equals to 9.81, PV is equals to 15.4 kilonewton. So P can be calculated as root of 9.81 bracket square plus 15.4 bracket square. So it is 18.26 kilonewton. Now the force in which angle it is acting, it is nothing but theta, and that theta is nothing but tan theta is equals to PV by pH, and therefore theta is equals to 57.48 degree. Theta is nothing but 57.48 degree. Similarly, this is one another problem. A liquid of surface, the specific gravity 0.9 is filled in a container shown in figure. Upon a depth of 2.4 meter, determine the magnitude and direction of hydrostatic pressure force per unit length of a container exerted on its vertical face MN and curved corner NQ. Now this is the problem of combination of two surfaces, vertical surfaces, inclined surfaces, and here again the liquid also somewhat different. For vertical surface MN, we know that pressure force P can be calculated as W into A into X. Now here W is nothing but 9.81 into or specific gravity has been given as equals to 0.9. Specific gravity has been given as equals to 0.9. So it is nothing but 9.81 into 1000 into 0.9. Now area, here area is nothing but Mn into unit length. Unit length we are considering because we don't know what is the depth of this container. So we are going to consider as a unit, and therefore it is nothing but 1.2 into 1 meter into x bar. X bar is nothing but for vertical line purpose, it is at the midpoint. So it is Mn by 2. So it is 1.2 by 2. So therefore vertical force purpose, so vertical surface Mn purpose, the intensity of pressure acting P is equals to 6.357 kilonewton. 6.357 kilonewton. This force acts horizontally towards right, and its point of application is given by h bar is equals to Ig plus Ax square, Ax bar plus x bar. So again Ig is nothing but here b cube by 12. So it is 1 into 1.2 cube divided by 12. So by that it is comes to is equals to 0.8 meter. Now consider curved surface NQ, that is vertical surface purpose. We have seen number of problems. Now consider this is a curved surface NQ. Horizontal component of hydrostatic forces on curved surface NQ can be calculated as UQ. It is given on the UQ, and it is nothing but pH is equals to weight into projected area into depth of center of vertical projection. So weight W into UQ into unit length plus depth of center of vertical projection is nothing but VU plus UQ by 2. VU plus UQ by 2. So it is nothing but 1.2 plus 1.2 by 2. So it is nothing but, or we'll write at values at here only. So it is nothing but W is nothing but 9.81 into 0.9 into 1000 plus QU 1.2. Depth we have considered as in unit 1 into VU is nothing but 1.2 meter plus UQ by 2 is nothing but 1.2 meter by 2. So pH can be given as 19.07 kilonewton. Now vertical component, again weight of liquid contained in a portion MNQUV. This is called as a complete force weight is considered at here. So it is nothing but rho G into volume of MNUV plus volume of NQU, as we solved previously. So it is nothing but W into volume of MNUV is nothing but width into depth. So it is a square actually. So 1.2 square into unit length is 1 plus 1 by 4 pi into NU square, that is R square into unit length. So it is 9.81 into 0.9 into 1000. How it comes? 0.9.81.9, because specific gravity here given it is equals to 0.9. So it is nothing but density is nothing but 900. So instead of putting 0.9 into 1000, you can put 900. So it is nothing but 9.81 into 900 into mn into nu, that is 1.2 into 1.2 into unit length is 1 plus 1 by 4 pi into r square is nothing but 1.2 square into 1. So PV can be given as 22.7 kilonewton. So the resultant pressure forces P can be given as root of PH square plus PV square. PH is nothing but 19.07 kilonewton. PV is equals to 22.7. So P can be given as 29.65 kilonewton. This is one another hemispherical problem. A hemispherical projection of diameter 0.6 meter exists on one of the vertical sides of a tank. If the tank contains water to an elevation of 1.5 meter above the center of the hemisphere, calculate the vertical and horizontal forces acting on the component. Now this is one side of tank where hemispherical end is connected, having the diameter of 0.06 meter and depth of immersion from the center is 1.5 meter. So vertical forces PV is equals to PV1 minus PV2. Now here PV1 is nothing but weight of volume of water MNST, weight of volume of water MNST minus weight of volume of water LNST, that initially requested when subtract. So weight of water of container by the hemispherical element is equals to W into 1 by 2 into 4 by 3 pi r cube. So it is nothing but 0.555 kilonewton. For horizontal it is nothing but W into A into x bar. So it is nothing but 100 into 1000 into 9.81 is nothing but W. A is nothing but pi r square, that is pi into 0.3 bracket square into x bar is nothing but at the distance of 1.5 meter. So it is equals to 4.16 kilonewton. Okay, so here we ate the all four types of submerged bodies immersed in a liquid or fluid. Now in next lecture we will start the next part of this chapter. Thank you very much.